I don't know where it is.
It's next door.
Oh, there's one next door?
Yeah.
Oh.
All right, so a couple of announcements. So just a reminder, so everyone should have received the final, and so then the final exam, sorry. There we go. I have to fix my Wacom mapping, sorry. It should be good. All right, so again, just a reminder that the final exam is ideally due tomorrow, so Friday, not tomorrow, geez. So I know, I keep mixing up both my classes, and I keep saying, like, I was telling my 200 level all about Wednesday, we're going to do all this stuff, so all screwed up on the days. So Friday, ideal at 5 p.m., again, that's physically. And if you can't make it in by this time, either, you know, you need a little extra time or just can't make it in physically, then make sure you email me just to let me know, and then you'll also have to submit it by email. And then that goes for any work that's lingering. So I'll just say, we'll call them paper assignments. So anything that you want to turn in as a physical copy should ideally go in by Friday as well, so this Friday. And if you do leave something next week, just email me, but I would prefer that if you don't get it in by Friday, that you then email anything else. So you can just email me, I'll just call them straggling assignments. And we'll say by June 13th, again, right at approximately midnight, but try not to wait till the last minute just so I'm not scrambling to do grades.
Where's your mailbox at?
So the mailbox, they're all on like the 3rd floor, so you go through the main office suite, and then mine is on the far side by the windows, and you should just be able to find it. So yeah, 3rd floor, mailbox. Let me know if you have trouble finding the box, but once you walk in, the secretary can help you find it as well. But yeah, the office closed by 5 p.m. though with the automatic doors. And I think that's it. Everybody showed up for the lab finals. That was great, so excellent there. I don't think I have any other comments. I think everybody made up the labs, so I think we're pretty much set. I'm feeling good about your class over here. All right, so let's do the demo that I had mentioned that we would do today. So again, just kind of refreshing our electrolyte solutions and going back to these ideas of what is a strong acid, what is a weak acid, and what does that kind of mean physically. And so let me swap over here. And I'll also put it over here so y'all can see. And so we're just going to test a few different solutions with our light bulb. So similar to what y'all did in lab. Uh-oh. I may need to run and get an extension cord. Let me see. Well, maybe this will work. Okay, there we go. All right, so y'all did this in one of your labs, but again, we're just going to repeat it with a few more substances than what you did. Oh, and I forgot to grab paper towels. Let me go run and grab paper towels really fast. All right, so we'll test, like I mentioned, let's start with water, and then I brought sugar, a bunch of pickling salt, and then we'll look at the bases, so sodium hydroxide, hydrochloric acid, and then we have acetic at the end to compare. So let's just do water. And so again, you did this in lab, so you kind of know what to expect. So unless our water source was, full of ions, then okay, we don't expect it to light up. So that's what's happening. So, okay, that's expected. Let's move on to sugar. So again, we remember sugar is a molecule, covalent compound, non-electrolyte. Again, let's just kind of verify. All right, nothing happened. Expected. Let me just rinse this off. Oops. Okay, and so then our salt, just so we remember, moving down the line here. So now sodium chloride, right, disassociates two particles, okay. So that lights up, but that's, again, what we did in lab. So not too unexpected. And so now let's go over to the strong base. And so I'll pour it in. So this is sodium hydroxide. And this is 3 molar. So I try to pick the similar molarities for the two acids and bases. So we have sodium hydroxide 3 molar hydrochloric acid, and then 4 molar acetic. So that'll kind of give you, again, a sense of their relative disassociation. So trying to get that clean. So let's look at sodium hydroxide. And so nice and bright, right? And this should be what we expect. So again, sodium hydroxide, strong base, so fully disassociates. So that's what we expect from our group 1 and 2 hydroxide compounds. All right, so drying that off. So now let's move on down the line. So this is hydrochloric acid, 3 molar. So I expect it to light up about the same brightness as our base, because again, they have the same concentration of ions then, and they both dissociate into 2. If I picked magnesium chloride, right, it would be the 3 molar would have more ions. Make sure that's clean. All right, so now acid time. Again, nice and bright, right? What we expect. So HCl, strong acid, fully disassociates. So again, we see that with that nice bright bulb there. And so now, what do I do with that paper towel? So now we'll do acetic acid. Oops. Make sure that's clean. So last one. So like I said, this is 4 molar acetic. So if this was a strong acid, right, then we would expect it to be brighter than these two. Let's see what happens. And so our acetic acid. And so look at how dim that light bulb is now, right? So now that's telling you, okay, unlike, again, our strong acid, where all those ions are dissociated in solution, there's some equilibrium where even the 4 molar has less ions, right? So again, that goes back to the pKa and blah, 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 all that strength. But I really like seeing it with the light bulb, just how dim the acetic acid is. So that kind of gives you, like I said, another sense of that, at least in a physical perspective. Let me unplug this before we electrocute ourselves. And then let me hook back up this bus. Too many things. All right, so again, we can just kind of recap what we just looked at versus what we went over in lecture. So again, right, it's all right here. So we saw how HCl was that strong acid. It really lit up that light bulb. So again, complete ionization versus the acetic acid, where again there's some sort of equilibrium, and so some of that acetic acid, right, was still, or a lot of it was still associated, and hence why the light bulb was so dim. Questions on that? And so now that brings us to this section, which is a good kind of build off of the demo. And so now we'll kind of go through all these words together and decipher what it says. And so let's kind of take it piece by piece. And actually I'll start by, I like doing this sort of analysis with it. And then you'll see once you repeat it and do this process a few times, you'll like learn which is which. But like I said, I don't even know if we're going to be tested on it. I would have to look at your final. But you should at least still kind of appreciate this process. All right, so then it says for these, so let's break this down. If the salt cation is the counter ion of a strong base, okay, so we're saying our cation, so let's look at this first part. So sodium, all we're saying, so I kind of break this up in its two components because we're trying to figure out, is the cation, basically we're asking, is the cation acidic or neutral? And then is the anion basic or neutral? And so I only make those distinctions because, again, if we go back to kind of our hints, sorry, I have to find where they are in the notes. So we have these general trends, right? So we already established that cations tend to be either acids or nothing, so acids are neutral. And then anions, right, we mentioned that anions tend to make better bases. So that's kind of why I'm framing it already in that sense. And okay, so now let's look at sodium. And then, again, they asked us, the salt cation is the counter ion of a strong base. So basically, did it come from sodium hydroxide? And yes, right? So you kind of try to pair it with the easiest hydroxide pair. And so, okay, it came from sodium hydroxide. And we know sodium hydroxide is a strong base, right? We just saw a demo to remind us. So this is going to fully disassociate. But what this is saying, right, is it can't reform like sodium hydroxide or do anything weird, or so sodium is not going to go and react, right? And that's because, again, we have this arrow here that's telling us it's all disassociated. So that's it. So that means that sodium, since again it comes from this strong base that's fully disassociated, so that means Na is neutral. And then we can do the same analysis for chlorine here. And let's read it what it says. So it says the anion is a conjugate base of a strong acid. And so again, just try to pair it simply up with like hydrogen. So most of these, right, you're just trying to like think simply. And so, okay, let's go through that. So chlorine then, or chloride, so is from HCl. And then again, we know HCl is one of our strong acids, fully disassociates, which again, all that means is that chlorine is not going to react with water to make HCl again in solution, right? That's not going to happen because we mentioned it is such a poor base, right? That was also kind of one of our other sayings. So if we go back, I think it was, where was it, that saying? Trying to find it in the notes where it was basically like the stronger the acid, the weaker the conjugate base. No, I can't find it. Should have been on page 2. Oh, this one, sorry. Right, so remember this saying here, so the stronger the acid is at donating a proton, the weaker the conjugate base. So that's where we're at with HCl, that our conjugate base is so weak that it's not a base, so that it doesn't react. So that means our chloride is also neutral. And so then that means that sodium chloride is, again, right, overall a neutral salt. And so then we can kind of repeat this analysis. And so again, the more you do it, the more you kind of remember who's who. So let's do calcium nitrate. So again, I'll do a similar analysis. So calcium and nitrate. So calcium, of course, comes from calcium hydroxide. Again, right, that's a strong base, fully disassociates. That's what I'm showing here with my single-headed arrow. So that means that calcium is neutral. And then we can look at the same thing for nitrate. So nitrate comes from nitric acid. And so that was one of our strong acids listed. So if we go back to here, and I forgot to print this, so I can do this while y'all are quizzing. But again, right, nitric acid there, strong, fully disassociates. So that means our nitrate, right, cannot reform nitric acid. So our nitrate is also neutral. So then our calcium nitrate is overall neutral there. Does that make sense for these analyses?
So when it fully dissociates out, that's when it's neutral.
Yeah, because then you can't go back. And then, so let's go through the last one on these neutral ones, and then we'll look at where they're not neutral. So KBr, again, we'll kind of go through this analysis a little faster. So potassium, right, from potassium hydroxide. So that's strong, so that makes potassium neutral. And then bromine, again, HBr. So that's a strong acid, so our bromine or bromide is also neutral, so overall neutral. All right, so let's look at a scenario where it's not neutral. So the next case that it shows us is when we have our base, our anion tends to be our conjugate base, but let's look at what it says here. So it says the salt cation is the counter ion of a strong base. Okay, so that's still the same thing. So that's neutral, right? So we're establishing that like sodium, calcium, potassium, those are all neutral. But then, okay, our anion though is a conjugate base of a weak acid. So that means that our anion is basic. So let's look at that for sodium fluoride and just go through the analysis. So sodium fluoride, so again sodium, right, they said, well, that comes from our strong base, so I'm just kind of re-verifying that sodium is neutral, okay. But then fluoride, if we pair it with the appropriate acid, comes from HF, which if you remember, HF is one of those weak acids. And so now we're saying yes, right? If we have this equilibrium, then fluoride in the presence of water is going to react to reform HF. And then this is where it gets defined as a base because it also would make hydroxide. And so that makes fluoride then our basic salt. And so similar situation, if we look at the other examples given, so they gave us, so this is calcium acetate. You can recognize the C2H3O2. So calcium acetate, which again, I'll rewrite acetate like so we can remember what the heck this is. And so of course, right, this is from acetic acid. So we can do our analysis. So calcium, we've already established, is neutral. But then our acetate is from acetic acid. And again, equilibrium to form acetate and hydronium. And because of this equilibrium, again, we can say that our acetate ion in the presence of water will then reform our acetic acid and then leave behind hydroxide formally. And again, right, that makes it basic. So now acetate is considered basic. And so again, same thing, if we scroll back up, so then they gave us potassium nitrite, right, which comes from nitrous acid. And nitrous is again just a weak acid, so we can do this one. So I won't show the equilibrium unless y'all want to see that. But again, just showing that potassium is neutral. HNO2 or nitrous is weak. So therefore our nitrite is basic. So again, anions tend to be basic. And then if we look at our last rule, this is kind of what I was saying though, is like there's not that many options for amines. And so now we're looking at the opposite scenario. So if the salt cation is a conjugate acid of a weak base, and so we can look at this, except the only bases that we really work with, at least kind of in Gen Chem, is of course ammonia, or then we'd see any other like amine variations. So we could do methylamine, again from like Breaking Bad and making meth. So that just has a methyl group on there. I'll write that out better so you guys understand, CH3. But it has to be some sort of like nitrogen-based compound, so you really won't see too many examples in this class. And so again, ammonium comes from ammonia, or we're looking for any other sort of amine derivatives. And then our anion is the conjugate base of our strong acid, aka, right, this is neutral. Then our cation is acidic. And then the anion is neutral, so we get an acidic solution. But I would just kind of star this, right? So again, you're looking for ammonia or amines. And then this is another kind of like caveat, but this I think you would have to kind of explore a little later, because this is not the full and complete picture. But basically what we want to take away from this is sometimes you can have what's called a highly charged metal ion. And it's just generally something like aluminum is in this 3+ oxidation state. So that 3+ just kind of makes it acidic. But again, this really isn't the full and the long of this story. Yeah, not to go down the rabbit hole, but basically like aluminum can bind water and it can also bind hydroxide. So it's very pH dependent, and you can kind of change the solubility, kind of pushing it around to different compounds as well. And so aluminum can have a bunch of different behaviors, but like I said, this is kind of a very general statement, and you can take that, but like I said, metal chemistry gets a little bit more in depth there. All right. Oh, and then again, this is kind of for your information, but we're not going to go there in this class. So what if you were looking at ammonium fluoride? And so if you look at this, obviously, right, ammonium is acidic and fluorine or fluoride is basic. So then it's like, well, how do you know which one dominates? And so it goes through. So HF is a stronger acid than ammonium. And so basically, we're saying that the Ka of ammonium is larger than the Kb of fluoride. But like I said, this is kind of beyond this scope and goes into other things. I'll give you this relationship. So Ka times Kb equals our Kw. But again, we're not really going to go there in this class. You could calculate this, right, if you're interested. We could talk about this later, how to go through it, but just know that, right, you would compare the relative strengths, and we can always talk about it more if it comes up, but this is more detailed. All right, let's try these examples. So see if you can determine if these salts are acidic, basic, or neutral. So kind of look for those hints. Don't get intimidated by this thing. Just figure out what it probably is related to. And we'll go over them. So what do we think for strontium chloride? Do we think acidic, basic, neutral? We could also go through one half at a time. No guesses? So what's strontium from? What base is it paired with? So what group is it in? So it's a metal. What group is it in?
Group 2.
So group 2. So right, strontium hydroxides, we said our group 1 and 2 are typically, right, they're going to fully disassociate. So okay, that means strontium is neutral. And then what about chloride? What do we remember? What acid is it from? HCl. And then is HCl strong or weak?
Strong.
So strong, so that means that chloride is not acidic if it comes from, because right, it comes from our strong acid, so then chloride is remember, fully disassociates, so what happens? Neutral, excellent. So right, remember, it can't reform, it can't do anything, so it's just stuck there. And so then, yeah, strontium chloride overall is neutral as well. All right, so B, so don't overthink this one. What do we say about aluminum? Acidic, basic, or neutral? So acidic, good. And, I mean, you know, they could have tried to confound you by picking, like, I don't know, aluminum fluoride, but we wouldn't go there in this class. That would even be difficult to approach in any course. So acidic, again, just from our highly charged metal rule. What about C there? Try to give you a hint. What was this thing, or what's it related to essentially? It's an amine, so right, it's ammonia or ammonium, so this is now methyl ammonium, right? So very similar to ammonium, it just has NH3 with a little group on there. And so I'll rewrite it out. But then what do we remember about ammonium or any other derivatives, acidic, basic, or neutral? So remember, cations are also either acidic or neutral, so that helps. So then this is comes from a strong base too. You could also think about the opposite reaction that it does, right? So remember, it has an extra proton, so then in solution, right, water is going to come pluck this off and reform our hydronium, right, our H plus, aka acidic species, and then of course reform whatever amine. But because we made acid hydronium, then that makes it acidic. So don't forget, right, cations are acidic or they're neutral usually. And then nitrate, so of course that was neutral, again from our nitric acid. And so making this overall ammonium nitrate, or methylammonium nitrate acidic. And then last one, or sorry, last one, since we already basically did that one. So what about this NaCHO2? So do we get acidic, basic, or neutral? What do we remember about this? What's sodium at the very least? So sodium's neutral, and then, so admittedly, right, the CHO2 could be tricky, and so this is supposed to be formic acid. You could look at, let's see if this chart gives you some inspiration. So it is over here, formic acid. So again, very similar to acetic acid. So right, it still has that carboxylic acid group, acidic proton there, but there's the other hydrogen. But all that is to say, okay, it's a weak acid, right? Equilibrium, and so formic, weak. So then again, this makes it acidic, basic, or neutral then for our formate. So what do we remember about anions? Basic, excellent. So right, again, anions are either basic or neutral for the most part. So then, yes, from a weak acid, basic. Excellent there. And then, like we already went over, obviously we compare the Ka to the Kb, but that's kind of a little beyond this course. You can at least appreciate you can do that. And then, so we'll just kind of quickly look at this titration. I think we've gone over it. So we did a titration in lab. So kind of a weak acid and a strong base. And obviously you saw the equivalent point. If we had a polyprotic acid with several hydrogens, then we would have multiple equivalence points like so. But again, this you would get into this more even like an analytical chemistry class, so not even 200 level, right? So trying to find every equivalence point. So. And then we already saw kind of our indicators in lab, so this is again just another chart. And obviously, right, wherever the transition is that you're interested in, that's what dictates what pH indicator you're going to want to use. Or I don't have the recipe at the top of my head, but there's something just called like universal indicator, which is just some mixture of all of, not all of these, but like I said, I forgot which ones are mixed in there. But that's a nice one because it gives you this whole like rainbow color all the way from, you know, 0 to 14. So 0 tends to be like red, and then you go up to 14 and it's like purple. And it has, like I said, the full spectrum. So there's some way to combine these such that it does that, but I could look at the recipe if we were really interested. But that's a good one. Again, just because I like having a universal indicator so you can actually know the pH. Otherwise, you have to already know where your transition is or whatever you're looking for. All right, in our last few minutes of class here, I just wanted to look and touch on some of the homework problems. And so first I just wanted to look and finish up with those pKa problems. So we had just kind of left off on Monday, right? I gave you this equation. I was like, this is it. We're going to use it. And that's basically all we need to know in this class. And then, so let me copy over the homework, or at least a screenshot. And so right away from the screenshot of this homework here, you can tell that it has, it's, I think, a slightly different, no, actually it didn't give you, oh yes, it gave you the formula, but it gave it in what I consider the flip version. So they gave you acid over base, so that's why it's a minus sign. But remember, I gave you the formula of pH equals pKa plus the log of base over acid. So they're the same formula. It just don't mix up. If you use a plus sign, use base over acid. If minus sign, acid over base. But then that's all we need to do is identify our acid and our base in these problems. So of course, in this case, right, acetic acid, well, that's my HA species, or my acid. And sodium acetate is A minus, or base. And then we can literally just plug it into our formula, and then I'll give you that the pKa of acetic acid is 4.74. So then we can do that for this first one. So 4.74 plus, and again I'm using base over acid, and they're already in molar concentrations. And so now let me just plug it into the calculator to show. And again, just good to do it on your calculator. Make sure that you're in the correct base and all those good things. Ah, sorry. And so then for the first one, I get 4.57 for my pH. And so then we can do the same for the next problem. Let me just look up our pKa values. And so I'm just asking the internet what our pKa of sodium carbonate is. So Na2, right, CO3. And so this one could be a little trickier because, again, we need to identify who's our acid, who's our base. And so the pKa for our carbonate is 10.33. And this, though, is our base, sodium bicarbonate, NaHCO3, is comparatively the acid. So again, we can plug in our formula. So plus my log of acid over base. I think I might need the pKa of bicarbonate. Sorry, I just wanted to double check the pKa value. and I can't find it. So yeah, we should be able to use this one. I think that will work. And so just plug that in. So 10.33 plus my log of 0.1 over 0.2. I got a different answer. Yeah, you should get closer to 10.6. What did you plug in? So 10.33 plus, did you do 0.2 over point, or 0.1 over 0.2?
I did exactly that.
Well, I feel like it should be closer to 10.6. I don't know what I've done in my calculator.
I did it back.
You,
0.2 over 0.1.
so if you do 0.2 over 0.1, yeah, I feel like something's a little off with our pKa values or something. Oh no, I think I was off here. Yeah, because this should be our base, so that makes sense. I plugged it in wrong. That was my bad. So I didn't follow my own rules, so write base, so 0.2 over acid, 0.1, there we go. So yeah, it should be 10.6 there roughly. The key has a different answer of like 10.55, but I'm not even clear how they got that answer, so we want to use, again, this formula. So on the exam, you have to remind me if you needed the pKa or anything, because that could be the only point of discrepancy. And so that's what's also weird about this one. So that's why I was taking extra time to look at this, because this is, right, a kind of different system here. So we have sodium carbonate, sodium bicarbonate, right, and then we can get back to carbonic acid. So we have kind of multiple pKa values there. So just, that's another caveat when you kind of just Google values, right? Make sure that you're looking at the correct transition. So just kind of watch out for that. And then I think the rest of the homework should be fairly straightforward. So just kind of glancing at the rest of it. So obviously, right, the conjugate base should just be differ minus a hydrogen. So all these, right, you just want to subtract a hydrogen. Same thing, conjugate acid, now you're just adding a hydrogen. This is a lot of solution stuff. We could go through some of these if you would like. I know we're kind of like running out of our official class time, so I don't know if you want to go over some of these. Remember the pH calculation, so pH of a 0.1 molar, right? We just plug our concentration in, so negative log 0.1 molar. So then we get a pH of 1 for 6 there. And then, right, the only difference with the sodium hydroxide is we calculate negative log of 0.1 to get our POH. So that's really the POH value. And then, right, 14 minus that to give you pH. So 13 there. Sorry, I can't write on the Word version. I didn't import it. And then that's about it. So of course the salts, I think that should be good on the homework. I just wanted to go over the buffer solution ones. Were there any other ones that y'all wanted to do together? Or are we just ready to take our quiz type thing? Or anything else? any last minute things we should touch on that were like on the final that are anybody stuck on, or last minute thoughts, samples? All right, I'm gonna hand out the quiz then from the silence, but don't be shy. If you have questions, you can always ask me after you take the quiz during recitation. So again, just ask me for help on the exam if you get stuck. I'd much rather you just ask me for a hint than, like I said, you just let it linger.